And the crazy part is, Uber's Michelangelo platform, the one they use for all their ML, handles something like 200 million predictions per second. Whew, 200 million!
Wow, that's almost incomprehensible. So we're not just talking about slapping a model onto some data anymore, are we? We're talking about a whole different beast.
Exactly. And that's what a lot of engineers miss. They focus on the model, the fancy neural network, the perfect accuracy, but they completely ignore the system around it. And that's where things fall apart. Your model might be 99% accurate in the lab, but if you can't reliably get data into it and predictions out of it at scale, it's useless.
So what breaks if you don't think about ML system design up front? And picturing a scenario where the data pipeline becomes a bottleneck or the model drifts and nobody notices until the recommendations are completely off.
Oh, it's so much worse than that. Think about Netflix. Imagine their recommendation engine, which is a huge part of why people stay subscribed, suddenly starts recommending only documentaries about 18th century pottery. People would churn so fast. That's a direct revenue hit. And it's not just recommendations. Fraud detection systems failing, self-driving cars making wrong turns, the stakes are incredibly high. The cost of getting ML system design wrong is massive, both in terms of money and reputation.
Okay, so let's break this down. What are the key components we're talking about? When you say ML system design, what does that actually mean?
Think of it as the full stack for a machine learning engineer. It's not just about building the model, it's about everything else. First, there's data engineering. This is about building reliable and scalable data pipelines to feed your model. Think about data ingestion, transformation, storage, and validation. It's the foundation on which everything else is built.
Data engineering, so making sure the model gets the right data in the right format at the right time. But wait, doesn't that mean you need to understand the data itself? Like the nuances of the data, potential biases, missing values?
Precisely. You can't just blindly pipe data into a model. You need to understand its properties, its limitations, and its potential biases. That's where data understanding and preparation comes in. This involves exploring the data, cleaning it, transforming it, and engineering features that the model can actually use. It's both an art and a science.
Okay, so we've got data engineering and data understanding. What's next?
Then, of course, there's model development and training. This is where you actually build and train your machine learning model. This involves selecting the right algorithm, tuning the hyperparameters, and evaluating the model's performance. This is what most people think of when they think of machine learning, but it's only one piece of the puzzle.
And I'm guessing even that is more complex than just running a Python script, right? You need to think about things like distributed training, experiment tracking, and model versioning, right?
Absolutely. Think about OpenAI training GPT-4. They're not doing that on a single laptop. They're using massive clusters of GPUs, and they need sophisticated tools to manage the training process, track experiments, and version their models. It's a huge engineering undertaking.
Okay, so we've got data, model. What's the next piece of the puzzle?
Model deployment and serving. This is about getting your trained model into production and making it available to users. This involves packaging the model, deploying it to a serving infrastructure, and monitoring its performance in real time.
So this is where things like latency and scalability really become critical, right? You can't have users waiting 5 seconds for a recommendation.
Exactly. And it's not just about latency. You also need to think about things like model monitoring, A/B testing, and continuous integration, CI/CD. You need to be able to detect when your model is drifting, deploy new versions seamlessly, and roll back changes if something goes wrong.
And all of this needs to be automated as much as possible, I imagine.
Absolutely. That's where MLOps comes in. MLOps is the set of practices and tools for automating the entire ML lifecycle, from data preparation to model deployment and monitoring. It's like DevOps for machine learning.
Okay, so we've covered data engineering, data understanding, model development, model deployment, and MLOps. Is there anything else that falls under the umbrella of ML system design?
There is always more. Another crucial area is monitoring and observability. You need to be able to track the performance of your models in real time, identify potential issues, and debug problems quickly. This involves collecting metrics, building dashboards, and setting up alerts.
So it's not just about monitoring the model's accuracy, but also things like resource utilization, latency, and error rates.
Exactly. And you need to be able to correlate these metrics to understand what's causing problems. For example, if you see a spike in latency, you need to be able to quickly identify whether it's due to a problem with the model, the data pipeline, or the serving infrastructure.
Okay, this is all incredibly complex. What's the thing that most engineers get wrong when they're thinking about ML system design?
Here's where it gets interesting. Most engineers think about optimizing for accuracy first. They want the best model, period. But the dirty little secret is that in many real-world applications, a slightly less accurate model that's easier to deploy, monitor, and maintain is often a better choice.
So you're saying that simplicity and robustness are often more important than raw accuracy?
Exactly. Think about fraud detection at Stripe. A super complex model might catch a few more fraudulent transactions, but if it's too slow or too difficult to debug, it could end up blocking legitimate transactions and hurting their business. They might choose a slightly simpler model that's easier to understand and maintain, even if it means missing a few fraudulent transactions. It's a trade-off.
That's a really important point. It's not just about building the best model in a vacuum. It's about building the right model for the specific problem and the specific context.
Precisely. And that requires a deep understanding of the entire ML pipeline, from data to deployment. It requires thinking like a system designer, not just a model builder.
Okay, so what are some practical takeaways? What should a software engineer do differently after listening to this?
First, think end-to-end. Don't just focus on the model. Think about the entire pipeline, from data ingestion to model deployment and monitoring. Draw the boxes, map the dependencies, and think about failure modes.
Okay, that's one. What's another actionable step?
Second, prioritize simplicity and robustness. Don't over-engineer your models. Start with a simple, interpretable model and only add complexity if you absolutely need it. Choose technologies that are easy to deploy, monitor, and maintain. Embrace boring technology.
And the third?
Third, obsess over data. Spend more time understanding your data than you do tuning your model. Clean your data, validate your data, and monitor your data for anomalies. Remember, garbage in, garbage out. The data is the model in many ways. Think of it like this. Your model is the engine, but the data is the fuel. You can have the most powerful engine in the world, but if you're feeding it bad fuel, it's not going anywhere.
All right, those are three solid takeaways. End-to-end thinking, prioritize simplicity, and obsess over data.
Exactly. Master those, and you'll be well on your way to becoming an ML system design master.
So if you're trying to build amazing ML systems, remember this. It's not about the model, it's about the system.